This is Generative Topologies V1, Fusion 360 and Grasshopper webinar. I'm sure you've all seen the website because you're here and you've joined, so you've kind of read through what's going to happen here today. And I just want to point out that if you haven't checked it out, our Design Morphine Masters, which is past early registration, but you can still register for regular registration. Got quite a bit of people already registered and joined, so it's happening and it's going to be a really great time. So definitely go check that out. Design Morphine Masters. Reach out if you have any questions about that. Tomorrow we have biomorphic networks with Madeline, which is a second iteration of the first one. It doesn't mean you've had to see the first one. It's a completely kind of update of the plugin, custom plugin for that webinar. And then 2 weeks from now, we have Fragmented Fictions, which is a Houdini webinar. And we have Elaborate Sinuosity, which is a Maya webinar. Definitely check those out if you're interested in those softwares. And after that, we have the CDNext4 conference, which you should also definitely check out. It's got a lot of great speakers and webinars there as well. So I will introduce here Zvonko. Zvonko has been a member with us for a while at Design Morphine, and he used to be a student of ours and is currently an assistant lecturer at TU Berlin. Zvonko is a computational designer currently based in Germany and working as assistant lecturer at TU Berlin. Previously, he was a research assistant at the Digital Design and Fabrication Department of the Brandenburg University of Technology in Topos. He has worked in offices in Germany and Denmark, most notable being 3XN in Copenhagen, doing computational optimization, fabrication of large projects. His interest lies in creating solutions for optimized and feasible designs, considering the environmental, economical, and social factors unique to the site and local requirements. In general, he's interested in the entire design reproduction process. He's been involved in many workshops, webinars, and lectures aiming to popularize the use of computational design, digital fabrication, and machine learning. So, without further ado, Zvonko, if you're there.
I'm here.
Yeah.
Thanks for the introduction, Mike.
And before I hand it over to Zvonko, I just want to remind everyone, if you have questions pertaining to what's going on in the webinar, then ask it in the Q&A. We'll be looking at Q&A for answering questions and answers. We won't really be looking at the chat for question and answers, but like kind of general conversations or conversations with each other, you should do it in the chat. Quickly before we start, question. Yeah, so we'll be using 360 here. Yeah, of course, we'll be using Fusion 360. It's a Fusion 360 class. So if you don't have it and you want to follow along, you'll need to get it, or you can do it later.
But you can still follow on the Grasshopper stuff. So
yeah,
it's independent.
Yeah. And someone's saying unable to run FroGh on my version. I don't know what version you're using. But I
have it on Rhino 7.
Yeah, yeah. So the website says Rhino 7. So if you're using Rhino 5, some things may not work. We can't guarantee what work on a Rhino from, I don't know, 8 years ago or however long, 6 years ago, however long Rhino 5 came out. So again, like we mentioned, Rhino 7 is free download. So that's the Rhino that we'll be using today. If some things may or may not work, we can't really keep track of what was working in 5 specifically.
Most of the plugins are quite old and have been developed when Rhino 6 was still popular or like the standard, but most of them have adapted or transitioned. So it might be with hiccups working, even in Rhino 7.
And then someone said having problem downloading Weaverbird for Rhino 7. So the way Weaverbird works with Yak, so it's not a download anymore. Basically, you just download the Grasshopper file from Weaverbird, and you just open the Grasshopper file, and that will install Weaverbird automatically just by opening the Grasshopper.
Or go to Rhino, go to the package manager from Rhino itself and search for Weaverbird, and you'll get it from there.
So you just need to open the Grasshopper file that's there, or any Grasshopper file that has a Weaverbird component. Okay, so I will leave it to you, Zvonko. I'm here. I'm listening. I'm going to try to answer questions along the way, and just call out to me if you need anything.
Okay. Okay then. So guys, first I'm gonna do a little lecture with you because there is some things we need to discuss. As you can see, I'm in my Corona lab right now with the printer and stuff. And first we're gonna do a little lecture how these things actually work and what is the meaning of all of this. So I'm gonna switch to my screen now and then just turn off the camera because it's quite unnecessary. And plus it's gonna get dark in an hour or so. And okay. So is it okay? Is it visible? Or so?
Yeah, I see your screen.
Okay. Okay. That's cool. So now, as we all know, this is the official poster. We're gonna be dealing with the intersection between Rhino or Grasshopper in that ecosystem in general, and how to run more advanced simulations and more generative, utilizing this kind of empiric generative design methodologies on stuff that we create within Rhino or within Grasshopper, or somebody gives us to us, and how to run these more advanced simulations that Fusion 360 or the Autodesk suite in general offers us. Probably for most of these, you can also do it natively in Rhino or in Grasshopper. You can also run these optimizations with Karamba or Millipede or whatnot. But I find it more straightforward and more professional, let's call it, to run it in Fusion, because it's much more industry grade, let's call it. Anyhow, so what are we gonna be talking today? So in general, the main theme is digital fabrication for manufacture, or for product design, or maybe even for general manufacture, for structural beams and columns and architectural elements. Everything can be done here. So I don't want to limit it to being only for product designers or mechanical engineers or whatnot, because professionally I'm not in any of these categories. I'm an architect, so but I have been dealing with these kind of stuff ever since I have been working at university, in our lab because we have robots and printers, and you eventually you would need new components, you would need new adapters, you will need some custom solution to fulfill what you have wanted to do or do it more efficiently. So like I got my experience in it. Let's call it, in this whole manufacturing world. And anyhow, so we need to like separate what kind of processes we have, what kind of, and how we can optimize these kind of processes, and then like how to generate like optimal solutions, or like optimal choices, let's call them, to from some generic empiric inputs that we have, like starting from the ultra basic needs, or what basic parameters that we need to achieve. And like, so like, what is digital fabrication? Like, I mean, I know you know what is digital fabrication in general, like most of you probably know what it is, but like we need to like run over what's the major point of it. Like, so everything you can, it's not, I mean, most people, like I know a lot of people that imagine digital fabrication as only 3D printing or something, but like digital fabrication is a whole larger scale. That, so it goes to this basic theory of like bits and atoms. So like you have some digital inputs, or maybe not digital, like you have some input parameter that you can call the bit, because that's the like your empiric input, that's your like base constraint. So like, and you're like, you have this kind of input and you need to construct a model out of it. You need to like make a, I don't know, a clamp that fits 3 screws and has like 2 outputs going to a pipe. I don't know, I'm just making an example. So like that's your general model, and how you're gonna do the design of it, it doesn't really matter. Like in the really rough sandbox mode, it doesn't really matter. Like, but anyhow, that model that you create needs to be sliced into a G code, whether that's a G code for a 3D printer or for a CNC, or like vector files for a laser cutter. That would be your production code. And like, so that we can code that the G code in some way, and that G code needs to go to the production machine, whether that's the printer or the CNC or the robot, it doesn't matter. That G code needs to be translated into like something that's physical. So we get some kind of a physical outputs in the end. And next, how do we actually start this process? So we have like, we're in the top now of this kind of graph, this chart, let's call it, and it's like, okay, now we have to make something. Okay, but what do we make it of? Like we have this kind of, we need to like first settle on the material choice, because that material choice is gonna affect a lot of stuff, a lot of design choices later on. Like, and we need to like constantly design with that material in mind, like how this is gonna influence our process further on. Like, and unless you want to be wasting some material, or like just doing it let's call it the non-optimal way, like then you're kind of free to choose whatever you wish. But in general, like mostly the 2 main categories, I would consider them as being like this kind of wood, plants, or natural based materials, and this kind of artificial, maybe not so artificial, but like harder, like metals or plastics, or all the composites you can gain from this, from the combinations of these. and like, and then we need to like go to the production method. And here we need to really like distinguish what is an additive and what is a subtractive workflow. So like the additive workflow is this kind of layering of materials. Like we have an extruder, let's call it, which layers on materials. Or it doesn't have to be an extruder, it can be something else. It can be also this, as we see, stereolithography, or this kind of binding on or laminating. You can this is also kind of in this civil engineering branch, like when you have this kind of laminated wood and stuff like that, but that's some kind of also an additive manufacturing. But there's also other this binding and laminating processes, and also like the most famous one being the extrusion, like, or in common terms called 3D printing, like. And on the other hand, when talking about the subtractive ones, we have these CNCs, like which have this kind of head, let's call it, this rotating head, which like literally pierces into a material and subtracts out of it. It literally a very destructive, subtractive workflow. And we have all of these kind of specific variations of that method, let's call it. Like either you do it by laser, or you do it by heat or electricity, or like there's also a water jet cutting and stuff. But anyhow, the principle is that you have this kind of material, you have this kind of giant block, and you turn it into a sculpture, however. And a special subset of these is doing the same things but with a robot, which the robot can do any of these if you equip it properly, with the right tools and all these adapters and whatnot. It can do all of these. And about these elements, these materials, they can be kind of used interchangeably between these processes, kind of, even though, for at least in my experience, the additive world has been more about the metals and the plastics and stuff. This right side in this chart, but like of course I have seen also people printing in fungi, mycelium, wood filaments, and all these kind of more natural soft things, ceramics also, maybe like some earthen materials and all of that stuff. So it's not like it's a hard distinguishment anyhow. But as you probably know, we'll be kind of concentrating more on these two like subsets, like how do you make it fit for extrusion, or eventually for a CNC, for like an subtractive, destructive workflow, let's call it. Anyhow, so but first we need to discuss what is there to optimize. Like what would be an optimal design in general. So let's say we have to make an adapter. We have a new robot in the lab or somewhere, and you need to make a new adapter for the TCP, for the head, like if it's like, if you want to call it colloquially. And you need to make it to hold a pipe or something else, something that's like it needs to be gripped, but not in a traditional sense to be like gripped. It needs to be held actually. So in the really dumb way, you would do it probably like this, which is like, if this is the, I want to annotate and draw on this thing. If this is your like TCP point here, here goes the head. This is the plane, and the plane goes here. Okay, the arm goes somehow like this, and you have it in some kind of extension that you can fit you can hold your thing here, and it just stitches with two like bolts and nuts, and this really classical system like this. Anyhow, this is the dumb solution to it, let's call it. But then you show it to your boss or to your professor or whoever, to the ones operating with the money, let's call it, and they will be like, this will take too much time to print in general, like, because if you want this to be held on a robot, and this robot is possibly holding a pipe that's like it's a concrete pipe for like spraying or so, like that's gonna be quite heavy, and like this needs to be quite thick and quite full, so there's gonna be like a big chunk of material going in there, like, and also the print is gonna take forever. Right? So the first like topic that you need to address is like how to make this lighter and how to make it cheaper, like production and economically wise cheaper. So like, the first thing you need to do is to minimize the economic loss, like, and then like, I mean, probably you can do that by using cheaper materials or like stuff like that, but like also a big chunk of it is like of that economic loss is kind of this ease of production, like how easily can you actually produce it. I mean, maybe you don't sense this too much if you're like doing this only for yourself, like if you just have a single studio with a single robot, and so you can have kind of the unlimited time to do this. But if you have a factory and you have to do this for like 10 robots or a lot more, like then it's gonna be kind of a time setback. So like, and also you need to like satisfy these kind of specifications, like in this case, like this needs to be holding a concrete pipe that's kind of heavy by default, or something else. Maybe it needs to like actually lift some heavier parts or do some other things that like they have some constraints that need to be fit or like satisfied in order to work, because that's the point, like we're making functional parts here. And like, and that's okay, like you go back to the drawing board, you experiment a bit, and at the end, like you run some optimizations and whatnot, like you will get to some results like this. So we have the whole structure, this whole bulkiness a bit reduced, but it's still bulky enough, let's call it decently bulky, so it can handle whatever the robot needs to carry away or to handle. So but still, this would be printing in a much less time if you set it to a proper material. This one was made out of ABS, if I remember correctly. And this would be the comparison, actually. You can see it's kind of also distorting the shape to fit the forces better, to fit this kind of engineering part better. Like in this simulations and generative design is quite often necessary to kind of accept the truths like of the solution. Like if you're just looking to get the prettiest or the most aesthetic looking piece, then you're gonna have like a hard time when you actually put that into motion and into practice, because like it might not fit the desired expectations, or it might not print properly. So like you really need to like think with all senses here, right? And now that we have this image in our head, like we need to start talking about what's the actual process of optimization. So like in general, like optimization is like kind of this approaches have been like by Brownlee in like 2011 in a paper, like which are like kind of this evolutionary optimizers that like in Grasshopper we know them like Galapagos or Octopus. They're also kind of called genetic optimizers because they are like doing this selection of, we have this whole pool of genes, we have this whole pool of possible solutions, and we make them kind of fight against each other. So like in each of these iterations, we have this process of kind of natural selection. So by the end of the iteration count or the iteration time, we have this kind of set of possible like survivors. That's called the possible solution space. And we have these other particles for optimizations, which are like more in a different logic according to this kind of natural movements. I'm not gonna talk too much about that. You can read it in a paper, like it was made by Judita. She was working with me in BTU. Currently, it's not currently, she said. And she made the silver eye, so like she made also this paper about these particle swarms. So but the main types that in our case we're gonna talk about is like this kind of single objective optimization, which is like, okay, we have only one goal and a lot of inputs, like we only want to minimize the mass of this thing and that's it, right? So that's the only single objective. But we can also have multiple objectives, which we're gonna see later in some other simulation, which we can say, I want the least heavy part, but also the one that's made out of, I don't know, titanium, but also like to make it more cost efficient. That's like already 3 objectives. So like we can have a lot of these kind of fitness functions that it's called a fitness function, and we can have this unlimited amount of inputs, and that goes to more towards a generative nature, because we have a much broader selection criteria, much broader. But anyhow, yeah, this is the general conclusion of that talk, and that looks like this for the multi-objective optimizations. So we have this kind of line, we have this kind of goal 1 and goal 2 on this axis, and we have all of these dots which represent this kind of solutions which are in this kind of space. We call this also the latent space. And this line, this is the perfect balance between all the solutions. So all of these which are close to this line are kind of equally balanced between these two goals in some way or another. So, and that is called the Pareto front. And this is only with two goals in a two-dimensional space. And in 3D, that looks like this. So we have like a ton of choices. And that's okay, but what does that mean? What does all mean for digital fabrication? So we first need to figure out the process, as I said. Are we going with an additive or a subtractive process? Or we want to run the optimization on everything? I mean, that's gonna take a lot of time, but we will know all the options then. Right? And we need to like design with us certain production methods in mind. Like, I mean, of course, we would have some favorite one. I mean, unless you're like, unless you have unlimited stocks or unlimited resources and machines to like do whatever you want, but most likely you would have a preferred method. So you need to like design with it in mind. And then when we get like what was it called, minimum feasible product or something, then we have that first iteration, we have to perform optimizations on it, and like then like refine it and select some final solution, let's call it. And then the first optimization in mind is, of course, the topology optimization. I mean, this is a really, really old method. Like this method has been like around like at least for 50 years. That like it's a really, really old computer numeric method, which is also a subtractive method. And so the point that it does, how it works is you just give it a chunk of material and you have all these constraints and borders and things to take a look after, and it subtracts from this whole chunk of material, it subtracts. So like this piece actually looks like this, like this in the back when you input it for the first time. But then if you imagine this as a, I don't know, shell holder or some kind of a structural bracket, you would have probably some forces going. Wait, let me just draw it. Probably you would have some forces going like this, and like it would be clenched like from this side. Of course, there will be some additional here, probably moments because of these forces and all of these things. But all of these data, the program needs to be aware of, so it can tinker around with it and like subtract. So we need to define like preserved regions and like obstacles and where the roads are and where the constraints are of this thing in general. And here you can see another like method, but here you can see how material has kind of a big importance in this subtractive methods, or in all methods in general. Like, but you can see the same thing made out of plastic and made out of metal. Like when you run the topology optimization, you would have these kind of two different results, even though you might have made all these kind of loads and constraints set like the exact same way, but the material properties and all these engineering constraints are, they will not be the same for plastic, for any plastic. Probably this is ABS or something. I don't believe they use POA for serious machining jobs. And you can see the difference. So the summary of the whole thing would be that we have this kind of sustainability and aesthetics increase, probably. Aesthetics probably, but sustainability for sure. And we also reduce the weight. That's certain. But the downside of these methods, it's like you will probably have a hard time like finding a complex shape to like make or like manufacture, or like to just get it into your decent liking, let's call it. And it's gonna be most likely quite expensive to do so. Like if you like this on the right, you need to either 3D print it or like machine it like with a robot or something, or like with a 5-axis CNC or something, which is kind of expensive. Kind of, I don't know, but I'm not in with the prices and stuff, so correct me if I'm wrong, but still, it's not an easy process as the left one, which you can just easily 3D print or injection mold or whatever. But anyhow, next one. Now we need to take a different approach. We're making this bracket, and this seems logical. Like this is what you would do like on top of your head. But then like we want to teach the computer how to do this, how to make this design better, but we're not giving him everything, because this is not, we're gonna throw the subtractive, destructive logic of topology optimization into the water, and like we're gonna like just give him the basic inputs, the ultra basic inputs. Like this, it needs to, we know from pure logic that this needs to be preserved, and this whole also, but I'll do that with another color. These need to be preserved, and these in the back also, they need to be preserved. And we also need all of these in the pose in the back to be also preserved, like as a boundary, actually, not preserved, but the algorithm needs to know that this needs to be empty in all cases, because we need to fit in a screw or whatever inside. So this is the only thing, and there's also some more here which we don't see. But this, so the system needs to has only these as its inputs. That's all it knows, and probably also that there's a huge plate here as the bounding box that it need, because we don't want it to like go on all sides. After all, there has to be some physical constraints until like which boundary it can go. So probably this whole boundary will also exist, like kind of this bounding box, which is also kind of hollow inside, or however. So yeah. So as I said, like we have this kind of preserved regions, we have the obstacles, and then comes again this engineering part with the loads and the constraints and the material properties, and that whole part still exists. And let me just clear that. Yeah. And then when we like run it through, we gave our system like that, we run it through, and we get something like this. And this shows no signs of having this kind of deductive matter. Like we can see that it has been built from the ground up. Like you can't do this like on your own. I mean, you can, but it's gonna take you quite some time. Like, and you can see all of these connections are built like with all these parameters in mind, all these loads and constraints and whatnot, and also these material properties. And probably you would never make it in the time the algorithm would make it, probably. So, and this would be the comparison. Here you can see the actual destructiveness of the topology optimization and this kind of smooth, polished, like intended design, I call it. This is kind of an design with an intention to be like this. It's not just like taking it out of something, trying to making it better. And this is making it from the ground up, totally anew. So, okay, now we did our part, at least digitally. So what do we need to do like before starting production? Or maybe you just like received a part from somebody which said like, okay, I have this part, how could you like do it for me? And the obvious thing would be like, okay, we decided on the design space, we decided on the material, probably because of X and Y reasons. We're gonna talk about the infill and the contextual parameter tweaking in a bit. But first, like I told you, like you received apart from somebody. Okay, I hear you're good at this stuff. Could you please lightweight this for me? And the part looks like this. And you're like, but what is there to optimize here? Like, you can subtract anything from this. You can like obviously like you need to like make it the whole thing from scratch in order to optimize something. I mean, because this part was also like obviously made for this kind of injection molding techniques and such. So like not too much could be changed in general here. So you need to like remake it as a generative design or something, which you could do. Like, you know, as I said, like maybe you would make these parts as the ones that we need to keep, or this one, and this other thing can be the boundaries, the voids, and all of that stuff. As I explained like earlier ago. And then you do that, okay, but then you arrive to your part and you start making these infills and stuff. So as I said, like there's also kind of a deal in it too, because like there is no silver lining or silver bullet for like deciding on which infill structure you're gonna use. I mean, in most cases, if you're doing small stuff or like models like figures or something that's not gonna be too susceptible to extreme forces or load bearing or shearing or whatnot, like it doesn't really matter too much. But if you will make mechanical parts or like parts that are meant to be under stress and loads and stuff, this is a quite an important topic, because in this case you see like it is kind of linearly evenly adjusted, but like when I apply, if I imagine this as a part that has some handle going like this, let's say, and there would be a force that would like twist it like this or something. This straight lattice might like start to crack. Might depends on a lot of factors. So it's much better to have like an alternate way of latticing, or like infilling in general. It doesn't have to be a lattice. It can be just like a straight fill. This kind of grids and lines and stuff. So it's much better to have a structure like this, where like everything is aligned with the forces that you're like proposing to this part needs to like obtain or like withstand, actually. And that's why I'd say like it's much better if you have, I mean, in most software, by default, when you have this thing and it just like makes it like by default something like this, really straightforward. It's much easier or much better, like structurally if these parts are like adjusted towards these lines or towards these projected forces. And you can do this like in Rhino and Grasshopper. I don't think you can do this. Probably you can do this quite if you like script it yourself. But I know you can do this like with more powerful tools like NetWeb or like, I haven't used the actual Fusion 360 capabilities for printing. Like I haven't yet used its slicer. I want to try it out, but never mind. Like that's the general point I want to say. So and that would conclude the lecture so far. And I can give you like some minutes the break before we jump into like Grasshopper and stuff. I mean, let me just reshare my stuff. Let's see if there's this. Let me add. Let's see. I'm answering some questions now. So, do you think implementing topology to a similar Fusion 360 workflow for topology optimization is a good idea? Should it be better to pair topology with Rhino? I haven't used topology. I know it, and I have wanted to try it, but I haven't used it. And but in general, like if you like, I don't know actually, because I haven't tried it out. I don't know what it offers, but probably it's a matter of how they optimize the structures and stuff, because like the algorithm should be the same everywhere. If you know the basic algorithm and how it works and what it can do, like it's just a matter of I know, like I disabled my screen sharing for a bit so I can like switch to the Grasshopper and stuff. So so as I said in the beginning, like I started like using Fusion out of making like not making dump, let's call it, parts for the robots in the lab or for the all this equipment that we had in the lab, because like it's a much faster thing if you just like do the empiric inputs and let the system decide on it, because like, or maybe just because like I'm a lazy person in general. I like to take the fast way out.
Yes,
So it's
Zvonko, should we let them take a small break while you switch to your other screen, or
yeah, yeah.
how
That's
long
what
do
I
you?
said. Because I'm
Oh, okay, so they're taking a break, right?
yeah, because I'm switching and I'm opening
Okay.
stuff. So and plus they need a break from listening to me. So I know my students need that too. So can you count the anisotropy of the parts? Yeah, I mean when you get the generated parts from Fusion, you have it as a model. So like you can run additional simulations on it. You can do whatever. Like there is like other simulations for stress or for for behavior, for all this kind of engineering nerdy stuff in Fusion, or just like load it in somewhere else, wherever. And right. Hey Yannick, like I remember you. Like we were in Rotterdam together. So
They're asking like how long is the break?
yeah, like we can start in like 2 minutes or so.
Yeah.
Just right. Let me just stand up and just open Rhino and Grasshopper. We'll just start with Rhino and Grasshopper. Okay, guys, like you're here. How do you install FroGh? You just like copy it. Where was it? When you get the file. Then this zoom bar is messing with me. I can click on it. When you go to the, where's my pro? Yeah, it's in the libraries. So what I gave you, like the libraries. Yeah, you just drop it in. You just drop it in the libraries. So like special folder components and stuff. You just drop it in. And also for the TriRemesh, you need to like, you get the TriRemesh because it's a modified version of the Kangaroo, like from the.
I think they were saying that the newest Rhino 7, the TriRemesh is, I think there.
Yeah, I mean you, but do they have it as a component?
I think they're saying it is, yeah.
Yeah, because like I didn't have it as a component anyhow. For those who have it as a component, that's fine. You don't have to deal with anything. But those who don't have it as a component have to go to this. You need to like paste it here in this where actually Rhino is installed. Where was it? Rhino 7 plugins. Where was it? Grasshopper components, and you need to replace the actual Kangaroo. And
So I think we might as well just get started.
yeah, okay.
And that's the TP1 file. That's the file you gave them, right?
Yeah, I mean, you can just open a blank file and start with me because we're gonna do it from scratch anyhow. You might only need these components from, but you can also get them from Fusion. I'll tell you what. So like, it's your choice. You can also start in a blank file. It's not file dependent.
Yeah. And also whatever we do here, we can save and give at the end too. Like whatever kind of like test or study you do.
Yeah. Well, what's anyhow? So, or
And they're asking you to put on bifocal.
yeah. Why?
So they're asking where this file is located. So maybe just to be clear,
I don't know, like
just to be clear, it's a new file. So just open a new Grasshopper file.
yeah, it's yours is called topos start point.
Cool. Okay, I'll let you
Okay.
get to it. Let's get through this thing.
Anyhow, so you can start with whatever you wish. It really doesn't matter. I'm gonna start with a torus. I'm gonna start with a donut. Okay, not that one. Torus surface. I'm gonna start with this donut. You can start with whatever you wish. You can start also like not with that one. I have also made, you can have a thing like this too, doesn't matter. But I find the donut more simple. Anyhow, we need this donut to apply some loads to it. This would be our point of optimization. I want this donut to be hit like I want to apply some forces, let's say here, here, and I will consider this as being some material. So we'll see how it would deform. So what did I do? Yeah, when you take a look at, because we're gonna be mostly working with topos now. That's my topos here. I just like, yeah, there. Like Control Alt and click and you'll get to it. So you see here in the topos that like you have these two parts like model creation, model data, and the solver. So we need to like make this into like a structural model first. And we need to like put some nodes, make some boundary conditions, and so at the end it would put out a model. This would be the end, let's say. So we'll get all of these components out. This you might not need, depends. And you will need the resolution for sure. Everything you can see here, actually. Boundary domain, condition, and the resolution. And this surface, we need to make it a mesh. If you wish, you can be as specific as you want. Like maybe like if this, we have this bounding box, I want to measure it by like taking out the first face, like faces by direction. Or you can also do this by like debrep and just picking the first face, I think, or the last. I don't remember which one was it. No. That's why I don't like this component. I never know the order of faces. So this is more elegant. I want to measure this dimensions. And right now it's 59 by 59. Okay, if that's centimeters, if you count that as centimeters, that's rather okay. Yeah, probably it also works. Yeah, I have plugged it here directly. And sometimes it might complain, but never mind. But now we need to deal with these kind of density values, modules, and stuff like that. So, and the manual way how to do this is like either you get in these kind of, either you Google it, what was it, in this material properties here, I have put you some links. So you can see the densities of major materials and all of these kind of structural properties. But I find it much easier just to like switch to Fusion. You don't have to do this right now because I have some ready for you, but in general.
Zvonko, that rep by service components, where is that from? Is that
Well,
Wombat?
I think it's Wombat. Yeah.
I think you didn't include that, so I'll just put it.
That's why I said like you can also do it like deep rep and just pick out the face. But that's only for measuring. You don't actually need it. Anyhow, where was it? I do this like just by going into Fusion and just doing like physical material. Not here. Manage materials. Okay. And here you have all of these, all of the materials. And let's say if I want it to be ABS plastic or any of these glass, metal, whoever, you can read all of these properties like Young modulus, Poisson radial, coefficients, densities, and stuff from here. Or you can like look it from one of these links that I showed it to you. But so here I have this kind of titanium 64, and it's explicitly chosen to be titanium 64 because like that's the most common metal to be 3D printed. That's the most 3D printable, not the most, but it's the most commonly used. So I can get those. This is a clue, and this is a clue. This is die 64. And this is ADS. You can do this for any material you wish. It doesn't matter. But what really matters is that you have to like convert the stuff in proper values. So if you have this kind of density value here, it needs to be in Fusion. I think it's another number. It's kind of a strange division, let's call it, but you just say it's 1 or 1.03. I think it was 1.03 density. No, it was on some of these links. Never mind. You have it here. But this Young coefficient, it has to be in gigapascals. Yeah, in gigapascals, in GPa. And in most cases, or at least in Fusion, you'll find it in megapascals. So you have to like divide it. And the division is like by 1000. So this is the thing. The density is 1.06. And the Poisson is 0.38. Yeah, 0.38. You can see it here too. And this would be our boundary domain. This is the latent space. And now we have to do the supports and the loads. We don't need this anymore because that was just for measuring. Oh yeah, we said that this would be centimeters because it was 68. In engineering and in mechanics, it has to be, it's best to work in millimeters. I mean, the whole world works in millimeters, the whole branch. So whatever you export, whatever you do here, you have to like be prepared that it should be in millimeters. So we need to like scale this, I guess. And the hack is, if this is in, and I'm gonna do this, don't, and then just switch it back again. Scale it by 10, okay, and then probably you can do the same thing with a scale in Grasshopper, but at the moment that's too much components. It's faster to do it like this. And just like re-reference it. Where's the, yeah, like density, like in Fusion, it's in grams, I think. No, I don't know, but like in general, it worked nice with 106. I mean, anyhow, we have our thing. It's internalized. Nobody can touch it. Okay. Now we do loads. I want to analyze this surface. So because it's a non-trimmed surface, I will just surf eval or eval surf. Like reparameterized. So we get the domain from 0 to 1. And I will put up not that bad, an empty slider. So I would put 2 load points. In this case, they are together. Okay, let's make it here. So to be apart a bit. And I'm gonna do a volume load because I want this if this would be one of those no, like not in meters, like you work with millimeters here. I mean, you work with newtons here actually in topos. You work in force. No, and I want a volume load here because like I want this to be holding a beam or something. Maybe this is some kind of these, you know, these mechanical beads or something. I don't know what's it called. In German, it's called the Mutter. When you insert a screw and you have this kind of ring that's like holding it. But anyhow, I want a volume load. So like on this point that we get, I will make a box, like a plain box. A box centered on a plane. And this would be our plane. A bit bigger. What did I put here? Okay. That should be enough. Bigger. Yeah, something like this to make it look logical. Okay. So these would be our load meshes. And these guys will be tracing. And now we have to like figure out if like smashing them with concrete or with steel or whatever. So we need to know the typical weight of steel or concrete or whatever. So like, not in this one, but in some of these, yeah, we have it here. Density for major structural materials. So we have like concrete, steel, whatnot. So let's say we're gonna like hit it with some concrete. So it's like 25 kilonewtons on square meter, on cubic actually, because it asks loading vector in kilonewtons on cubic meter. So, but this vector needs to be reversed first, because this is the x1, the plus z. And this would be 25. 25, okay. And this would be our load. But we also need the support too. And we need to say, okay, this guy will get the bounding box, let's say. And get the debug. Because some of you don't have wombat. Let's get the choose the bottom face. Not this one. This is the top. Okay, it's this one. This is the bottom face. Maybe just like extrude it a little bit. With some thickness. As a support here. Vector. So I put both of them. Okay, let's see. Just check. Also reversed. Okay, and this will be the support. And this is the load. Boundary properties, you don't really have to, I mean, you can, but like, this is these things like which mesh should be fixed, which mesh should be avoid if you're doing more complex stuff. But for now, we don't really need this. And the resolution is the actual like refinement of the simulation. In general, what have I put here? I put a resolution of 1. Just make sure it's like a floating thing, so you have control over it. And now it will calculate.
Hey, Zvonko.
Yeah, it's stuck.
Um, is out of curiosity, are you using the GPU topos or just
Yeah,
regular?
you can
Oh,
I'm using the GPU, but you can use the CPU too. It doesn't matter.
yeah.
Whichever works for your PC. So,
But like for instance, a process like that usually takes a while either way.
yeah,
Yeah.
depends. What's stronger on your PC? You can use that.
Yeah.
Nope. My GPU failed, so I'll just use the CPU. Where's my mouse? I don't see my mouse. Oh, it's still stuck. I have like a GeForce 1050 or something. It's like 2 years old or something. Let me just check. You know, it's the standard one that they're putting in most laptops, nothing fancy. No. Okay, topos doesn't like me today. Out of memory exception. Come on. But here it worked. Here it's okay. And here it computed with the GPU. God damn it. And anybody got to do it? How about I have an idea.
They did it.
Continue.
I wonder if it's because you have it computed above and now you're
Yeah,
computing
that's
it.
what I thought now, like running it in a totally clean file, if it matters.
Yeah.
Right. Let me just-
But a few people are saying that they got it to work.
Unless my memory will, if it's not too busy with all this stuff running around.
Samina said it. Samina is saying it worked, and she disabled your definition.
Ah,
So maybe it's because you were trying to do it twice or have it calculated twice or something that it ran out of memory. If you're using the topos start point file and also getting an error, did you save that file in GPU mode, Zvonko?
yeah, yeah.
Yeah, so if you're getting an error, you might try to switch to CPU mode because you
Yeah,
might
just
not have.
yeah.
Well, I'm just saying for Jesus, because you might not have the proper graphics card or graphics card powerful enough or with enough memory to use GPU mode. So you might have to switch to CPU.
No, it failed here too on the blank file. But anyhow, let's just roll. Right. I'll just roll with the upper one for the sake of convenience, since it's done. Anyhow, we are here. All of these we have done so far. Just let me just my photo. And now you get this model, and you need to set up these parameters. These are like Topos has this kind of Optimus engine, and there's also this analysis parameters. So like here you can set the iteration count, like 4,000 or whatnot, and also the tolerance. What is the actual tolerance between iterations? And
so
that
a good point. It might not be working because you're streaming, like because that's using probably a lot of GPU.
Yeah, probably because the error was like exception memory out of I don't know.
And then Jesus is saying when he switched to CPU, it's working. So
yeah, so if it's working for you, that's what matters. So like,
and then a few people got this invalid value. This indicates that one or more of the parameters passed to the API call is not within the acceptable range of values. Sounds to me like that would mean that the values are
too high. Yeah, I don't know. Did you like make more like right here? I made it for stainless steel because it's weights more. So here it's like 75, as was I think here. Yeah, 78. Okay, whatever. So it weights more, but all of this is all the same. With the instance that here I use the supports on both sides. It's not only the bottom. So, but the rest is the same. Like you just and find those, make them reversed, put some extrusion value.
So some are saying that it worked for them when they put the resolution higher, bigger.
Yeah,
so
probably.
like 4.
Yeah, probably.
So they put that to like 4 and it worked.
Yeah,
and that's not actually. You're not making a higher resolution by putting a high number. You're actually making a lower resolution.
Yeah,
You're making bigger pixels, basically.
Yeah. You're making bigger pixels, and you're your optimization is gonna be much more coarse. It's not gonna be as refined. But anyhow, you just get this model at the end, which is the actual calculation, the numbers. And now we need to make sense out of these numbers. So like we need to, as I said, get this Optimus. And when you get this Optimus, you have this kind of model, which you can like directly put it here, or you can just like put it through the analyzer, and then you can control the iteration count and like this kind of tolerance between iterations. And here, yeah, you can choose between pre-ensemble and matrix-free solver, but put it on auto. Like we're not really digging into the nitty-gritty, nerdy side of things. So for us, it doesn't really matter because we're just like exploring the workflow. And then we have this kind of Optimus parameters for this solver itself. And here I set it to be like 20 iterations and to reduce like 50% of this weight of the donut. And then you need to put 2 toggles for the reset and for the run. And you can either make it to run live, like to see each iteration, or you just see the last one, which is kind of faster because like it doesn't bother your CPU so much with the display of each iteration. I'll just put it on final for now. Yeah, then disable this. So it's okay. I know you don't have anything. Come on, disconnect. And we get our donut somehow. This is the iteration number 0 with the initial forces being hit on this donut. And you see it kind of a bit shaken, wobbly and stuff. Not like you need to reset it first. Okay, and reset it. Somehow it doesn't reset by itself, so it's kind of a manual process. And when you like run it, you should start counting the iterations. But we won't see anything now because I disabled it. Yeah, if you see something moving at least. Okay, it's done. And we get this benchy thing. So I would just like bake this for now. Put it on. Okay. I like this turntable mode. So let me just go and turn out the lights at my place. I'll be there in 2 seconds. Okay. You can also do this, like you don't have to bake it. You can also like custom preview. And we can still have it. And that's okay. What I want to do next with this guy, and that's okay. We have some result. I want to make it into a full-fledged table now, because the next step would be I want to send this eventually as the starting shape of a fusion simulation. Because I mean we have two options now. Either this would be the starting shape of a fusion simulation where we define all the borders and stuff I talked about in the lecture, or we continue doing it in Grasshopper as a lattice and all of that stuff. I would say we just make a simple cover, let's call it the top plate of this thing, and then send it away and see what it comes up. But first, this is still quite a rough mesh. I would, and here comes the TriRemesh. So it would give me a finer mesh to work with. And we get something more feasible. I mean, it's rougher, but you can also adjust that. If you count up like mesh edges. Give the length. What is the 1.72 and the lowest is tiny. Let's say we'll take the average on both. On this average. 0.98. Okay, let's optimize to this length. Looks a bit better now. Anyhow. But I also want to cut this guy a bit. I'm just gonna bake it. Pull it up a bit. But like, I want these to be rather flat, and plus they will help later this setting of boundaries and such. Let's say we're gonna do the front. I want it to be flat like this. You just extrude it. You see this little gumball here. You can just drag it. You'll have something to cut with. Mesh Boolean difference because it's a mesh. I want to subtract from this with this guy. And now we get it flat. You can also do this in Grasshopper, but like it's a 2-second job in Rhino. And we also want to have the top plate, as I said. So I just do the bounding box. Control Shift and select only the top thing, the top surface. Let's press copy. Go I for in place or click on in place. And you have the top surface. You can extrude this one too. And also like mesh boolean. Actually, I could have done this better. Why can't I undo anything? Okay, again. As I did, like copy I. I want this to be this border, and I will like rebuild it to some degree, so it would give me a more curvy shape. And the second extrude some tiny amount. Why does it do it in sub D? Okay, I have to intervene. This curve. Let's extrude it. Some amount. Okay, cap. That's what. See if it clashes. You can also like clash this. Yeah, they're clashing. So merge Boolean difference. It's flat. Nice. Cool, cool. We're all flat. Oh yeah, important note. To import in Fusion, it's best if you import poly surfaces. Oh yeah, Fusion works with meshes too, but like for the best experience and to not lose your nerves for when picking stuff, like use NURBS or use poly surfaces. Right? So mesh to NURB. And we can kill our mesh. That's okay, that's fine. Everything is flat. Now we can send it off. Just select it. I will just like bring it to the ground. Oh yeah, and we need to check the size. Let's check the size first. Because like when we go to Fusion, we want to be as specific as possible, like with real dimensions, weights, and all of that stuff. I mean, if we're considering this to be a proper table and not just some figure, because the results will vary also. Box. How big is this dimension align? It's 62. Okay. 47. Okay. Now I need to switch to display. So I will just do distance. 21. So this needs to be at least 40 centimeters or 70. Depends on what the world want to treat this table as. Just like, and now we can like actually morph it into a twisted box, or we can just scale it manually. Like one option is that if you just go and make a vertical line, like here you can just do a vertical and be like 40 centimeters. Just scale. And now the dimensions should be appropriate. So this is like 1 meter 20 already. And this is 90 centimeters. Okay, now it looks like a proper table, dimension-wise. And this will be 40. Okay, still a bit low. Maybe we can just like scale the Z on, but then it will like, then it will be not so nice. But anyhow, let's roll with this. It's rather okay anthropometrically. Okay. Is everybody here, or everybody just silently watching? I see a question. So in the chat, I see like is the ISO mesh? No. Yeah, actually I can just export this one.
You could put it in the same
Yeah.
Dropbox.
Export selected.
Some people are getting Rhino invalid operations accepted. I don't know. Are you using the not the Zvonko, for Casper? Are you using the latest Rhino 7?
Uh, small, save the geometry. Okay. And now when we get to the Fusion, and here I have all of these. I'm just gonna make a new folder here.
Hey, Zvonko, can you drop that file into the
Oh,
shared
yeah.
Dropbox?
Yeah. There's my Dropbox now. Oh yeah, I made a mistake. This needs to be millimeters. So I need to rescale it, which is not a big deal. So and yes. $900. That's proper.
think that's not the Dropbox folder.
I don't know. Or I can just put it here. Like,
I mean, the folder you have open is that's not like the Dropbox folder. That's what I'm saying. Oh,
but it's
So-
there. Somebody says it's there.
interesting. Okay, if it's there. Okay, yeah, table 1. Okay.
Yeah.
Now I see it. Cool. Okay, so it's in the Dropbox for anyone that is having errors.
Yeah. Should I post it here too, like in the chat?
Well, I think at this point they should have the link.
Hmm?
At this point, they should have the link. So
Yeah. Okay. Anyhow, let me just in here in Fusion, like you have also this kind of upload, and you can just like select the file or drop it there. The cool thing is like it supports Rhino natively, so you don't have to worry about a thing, which is really cool. It's there, yeah. The Grasshopper file should be the same. Like I haven't added anything substantial to the original one, except the TriRemesh. Nothing new, so it should be the same as the starting one. Weaverbird is just subdivision, and Weaver just divides and smooths. Like if you want true optimization, like you need to do actual remeshing, like TriRemesh or these. Like there are other ones like which actually do remeshing, not subdivision and smoothing and such. Now we get our table. We have our table in Fusion. It's so nice. I can close this. I don't need it. And first, what we need to do is to make the boundaries. Like if you define this to be the starting shape, like in general, like when you go to the generative design, you have this kind of preserved geometry, obstacle, starting shape, and stuff like that. So like if we can start it without a starting shape too, but for this table, we don't, if we just put it with, I'm gonna draw somewhere. I'll draw here maybe, or where's that? There was this share whiteboard. Where was it? Yeah, whiteboard. Where's my whiteboard? So in this sense, like if we have this in this table, we need to define stuff. Like we have our that didn't went well. We have our top glass surface, and we have our table underneath somehow, and we have to define these.
Zvonko, are you drawing?
Yeah.
Because it's
In
not
this
showing any drawing.
No? You only see the whiteboard?
Yeah, just the whiteboard.
Okay, so I'll do it in Grasshopper.
Yeah, probably better.
Yeah. Okay, so or here, but I can from Zoom. Yeah. So in this case, we need to like say, okay, I want to preserve this part, this whole top glass thingy. I want to preserve it, and I want to preserve these bottom faces because that's gonna be the link. But when you input this, and the boundary is gonna be, we can set it to be like all around, like we can just like put this into a bounding box and then like just boolean difference out of it, and this negative shell, this mode would be the boundary. So, but anyhow, if you just run it, tell it, okay, only these two things would be preserved, and the only force actually working is this, like the stuff you put on, which if you treat it as a normal table, like not somewhere in some industrial hall or whatever, it's not gonna be quite of a big load. So Fusion will be too, I don't know how to tell it, like too optimal, and he will say then you only need a column here and a column here, and you don't need much more to preserve these boundaries with these loads, which is not gonna be more than 2 or 5 kilos max if you're treating it as a standard table. So what I want to do actually is to use this stuff that we actually got from the topology optimization as the starting shape. So he would be from the start limited in which latent space it can work, let's say. And then we can say, okay, now my loads are actually, let's say, a load of a person. Like I need this table to withstand 50 kilos at least. So then somebody actually sits on it. I mean, unless you have fat friends and you need more, but like, so in that sense, like this would be something to preserve geometry, one body. Okay, that's it. And by the way, when you go to selection priority, you can switch whether you want to select the bodies, the faces, the edges, and stuff like that, which is really handy. And for the other preserve, we want this, but I mean, probably we can do that also like this, like, and just select the faces. Or no, it doesn't get. No, it's only the whole body. Okay, so we actually have to extrude this, which is kind of my mistake. You can also do that in Fusion. Like just let's see if it's not gonna be too much of a pain. I find Fusion really not too intuitive for hard modeling. I feel Rhino it's much better, or I'm just more used to it. And, but when you press E, no, I'm still in generative design. I need to switch to the normal design. That's why I can't. But then when you press E, you get this extrude, and you can extrude it. I want to select more faces. Some small chunks here. What's it, please? Oh, come on. Okay, that looks about right. E. And here you have to like select it to be a new body, because otherwise you have this kind of join and cut, these kind of Boolean intersections. I will just put it on a small platform like this. This can be also in the other way, but like, let's keep it simple. Not join. I want body. Okay. also here. Just shift and click through all of these. Okay, this went much faster. Not showing, just new body. And yeah, we have these separate. And also a big thing would be to make the boundaries from this thing. So we'll just like go to the back. Actually, we don't have to go to the back. We can just like create a box. You have to choose the plane. It's this plane. I'll just look it from the top. From here. This kind of bounding box. Not cut. I don't think. Now just move it a bit down because you see these guys. Move copy or M, and just drag it a little bit down so it would completely fall into the box. And then we put combine on this target body. I want to cut it. And we need to keep the tools, very important. We need to keep both. Okay, now it's cut. And to make sure it's cut, you can be like visual style and shade it with hidden edges, and you can see even if you move it like with M, you can see that it has been cut. Oh, I forgot to cut the table. You see, that's why it's important to make checks like this. Now it looks okay. And this would be our boundary volume. Now go back to the generative design. You can just and I just like answering the question in the Q&A. Like I just like I have this kind of default project in this whole, like in my, not this admin stuff. I have this default project. This comes with Fusion, and there your work is stored until you create another project. So like, I think this comes by default. I mean, and then like I just have all these folders and I just upload it and drop it there. I don't know. It has been this simple ever since I'm using it. I don't know what's your exact case. Anyhow, getting back to the obstacles. This would be our obstacle. This guy. And now we can, because it's too big, we can just like uncheck it so we don't see it. And we can continue. So we need to preserve this, not that guy, this guy, and this guy. This will be our things. And I want him to start from this. This would be the latent space. That is because in general, if there is nothing, it would be blind. It would be blind. It would be just like make a whole square and then try to like work with it. But in here, you're kind of helping it. And the results vary. Like I will show it to you on another example, a much simpler example to see what's the difference between having a shape or not having a shape. Anyhow, now comes the engineering part. Now we have to do the loads. Now it's gonna be simple because like the loads are obvious. The load is gonna be this. And we need to like specify it in newtons. Like in this case, we're like doing it equally on the whole plane surface, but you can be also like specific. Like do all these angles and like by axes or by specific stuff. Here, I think you can like put it on multiple, yeah. You can put multiple forces like with multiple radiuses on specific points. Like I want it to be only loaded here, 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 and here because there's not gonna be much going on in this area because it's empty. You can also do that with this angle. But let's assume that like this would be a general table and it will be used everywhere kind of equally. And we need to set a bigger, that's what we said. We're gonna make a bigger force. Let's say like 300 newtons or 400, which kind of equals to 40 kilos. It's by 10. You can also do really small forces and you will get really subtle results or like kind of obvious results. And you might not, you will, when you see it, you might not think that you would need generative design for that. So so this would be our only load so far. And we need to do the constraints. So we know that this guy and this guy is gonna be locked in all 3 axes. It's gonna be locked. So whatever happens, this is the shape, the starting shape. It needs to optimize this. I mean, not reduce, like literally just take it as a boundary in order to work with. And then these are it here, and that's okay. Now we need to like set the design conditions. It is available, right? I mean, I'm using it like educationally. I kind of have a student version too, so I'm using it all the time. So it's available. I don't know, maybe I don't know if that matters if because of the region or whatnot, but I don't know why should it matter. But educational licenses get generative design for free forever. Anyhow, now we're doing the setting on the constraints. But if they changed it, if it should be affecting me too, and I still have it. So or just make new accounts. I know I had like a I don't know. Try with a new account, I would say. It should work. I have it since like this account since I don't know, September or so, October. So it's not that far ago. And it's not 2020, that's July. So anyhow, moving on. You have to like make this kind of, okay, we did all of this. We need to do the criteria now. We say like, we're gonna minimize the mass or minimize the stiffness, maximize the stiffness. I would say minimize mass because like it's bulky anyhow. And the safety factor, right? It's an important constraint because like as low as the safety factor is, the lower it is, it will produce much more stringy organic webby shapes, which like might look nicer, might look crazier, but like when put to the test, like I'm not sure whether you can like actually print those and like be actually usable in real life. But just set it to 2 for now and see what it like comes up. And you can turn on these two. These are experimental for the mode of frequency and displacements and all of that. The buckling is only when there is like a single force, like a single force applied to something, and like from this single force, this kind of like twists and turns and like this kind of buckling effect. So like in our case, that's also kind of true. And like we can do this by 1 or by 2. However, put it to 2 just for the sake of example. On maybe 1, and then we can just like always backtrack the iterations. That doesn't matter. And important part is like you have to like make the manufacturing, and we do the additive, the unrestricted, and some milling. But in this case, I will do 5-axis milling. It's much more fun to look at. And plus, this table might be like milled by a robot at some point, if you imagine this as a whole block of something. And here in the overhangs, I will do more. I will do like 50 or 60 to get more crazy results. Because you can always regulate that in a slicer or by like subdivision afterwards or stuff like that. And the minimum thickness is 3. Okay. I would say 4. But for this kind of aesthetic things, I think 3 is also okay. But we do all axes, all the positive orientations. Okay. And then we need to deal with the materials. Yeah, these are kind of my most used ones. ABS is kind of by default. You can also set it by material, by manufacturing type, actually. Unrestricted is kind of default is aluminum, which is also okay because you can like use it in any case. You can print it, you can CNC it or whatever. I would also say the titanium is kind of in the same branch. But in the additive, I would add also the titanium, but also ABS and PET. And in the milling, you can also mill titanium. But I haven't seen a huge block of ABS or PET. So and now we're kind of ready to generate. You have this kind of pre-check that it says it might be too large to be 3D printed, but Fusion is kind of limited in its knowledge to the normal FDM resin printers. So it doesn't, it's still not aware that you can print with a robot or something. So I just ignore that and we're ready to press generate. And you see like it works for me, like education. I have unlimited credit. I can use it as much as I want. So, and now it does the thing. Is everybody here-ish? You have to start generative. So okay, you have cursed it. Today everybody hates me. Or am I missing something? I'll just like lower the force a bit. Not 400. Let's say we're gonna do 200. Because like literally this morning I ran the generative design. It was working nice. I will show it to you later. Okay. Or maybe because we just scaled it, maybe it was too big to be accepted right now. No. Okay. Let's try with a simple thing. I can show you the results of these. was it? This was the earlier one. Yeah, this was the. It's the same setup, same everything. And you can see some of the results here. I will just quickly flick through it because I will go to another example. You can see something totally morphed. In this. You can see the stresses and all of that stuff. Yeah, but still, I don't have a commercial license. I have an education license, which is probably the same as a student license. So and on to more simple stuff, or to the next step. So to get our hopes up, let's just do a simple shelf. And then we'll like just put it into the topology optimization and the generative design. So the one I sent you, the simple shelf, how was it? Yeah, this guy. You already have it. Yeah, it's this piece. And we're gonna like literally load this piece into the generative design. So I would show, so I show you what it actually means, and let's see if the hypothesis is correct that the generative design is down and it sucks. Let me see, how big is this one? Okay, it's like 15 centimeters or so. and 135. Okay. You all have this one. I don't have to do anything. I can close this. Where's my simple shelf? Simple shelf. Okay. I can upload it again. So we would be like on the same page. Yeah. Simple shelf copy. Okay. Let's drop it there. I wanted to show you how to like go forward with the Grasshopper part when this generative stuff is like actually calculating and such, but this has altered some stuff. So sorry for the freestyling a bit. I'm seeing a question like, is this gonna be printed without supports? Like, if it was for the titanium table thingy I showed, like it's generated that it can be like printed with, but of course you would need to add some minimal ones. I mean, of course, because there was some stuff hanging around as you saw, but still you can add like supports and like soluble supports or like these kind of new materials and technologies that you can like have this kind of dripping stuff. So it's not a problem anymore that whether if it can be printed. It can, but like you just need more different type of supports than the FDM ones, you know, this kind of PLA stuff that we're kind of used to.
You have a few around in your space there, don't you? Printed.
What? Ah, yeah, yeah, I have. Wait.
I don't know
It's
if you
done.
want to show them in the camera while it's
Yeah,
computing. Or...
it's done.
Oh, so yeah.
Wait, where's my camera? I don't know. I need to switch you on. Now it's dark in my place. So one of those brackets are this. This is from PET. And this is the generative design version. And this is the topology optimized version. But you'll see this difference better on screen. And this was one of the tables, one prototype of that table. but only one of these columns. Like this was like this somehow. These which I have around here on my desk. But I have the real ones in the lab, like in one-on-one. So anyhow. Anyhow. Okay. So you have this guy. I should have made like I need to make two holes here for the stitching for the nuts. I forgot to do that. So I'll just, you can do that also in Rhino by yourself and just re-upload it. I will just like make a hole here. You can make a hole. There is the hole component. Oh, yeah. I want it on this face. Not so big. This is humongous. Distance. No. We need like 2 millimeters or so. Yeah, like a tiny. Okay, maybe not 2, but let's be a bit. Yeah, something like this. You can make this as standardized as you want. I don't have the time to right now. Okay. So this guy is one thing. You can also do it like this. And then have the cylinder for the boundary space. And the body. Move. Okay. And I want this guy to. Not showing new body. Okay. And Okay, so this would be, oh yeah, and we need to do the box. Actually, here we don't need to do the box because that's the point. I want him to figure out what to put here. But here I don't have a shape to optimize. I want him to give me the solution because anyhow, we want to preserve this guy. The obstacles are these. And the loads are mostly gonna be on this plane here. And let's say and 5 kilos or so for a shelf. So that's like 50 kilo, 50 newtons or so. I don't know what did I put in the other one. The 24. Okay. Yeah, but I have also extended it a bit. Maybe I should do it here too. You can just do that. Or just run it like this, see what it says. And then for the next iteration, we can like extend it a little. But I will definitely like increase this force. It's 100. 110. Okay. So that's like 10 kilos or so. And we need it to be clenched to this, not loads constraints. This guy needs to be fixed. But now we have another structural thing to consider. This guy is gonna be loaded. There's gonna be a moment like being here, you know, like this very basic example from statics where you have this kind of swimming, what's it called? When you jump off into the swimming pool. So like you apply your force here, but it's also felt here. So you're doing this kind of moment of force here. So that needs to be also like taken into account. So this guy needs to be a moment. You have all of these kind of pressure, bearing load, remote force, all this stuff here. So if we have this moment and this like indirect force, if we set like hundreds, like we set 100 newtons, let's say this one is 50 or some, because you know like the force gets weakened as it travels. So like the biggest force is here, but here it's a bit weakened. I mean, I'm not a proper engineer, so if somebody is a proper engineer can really correct me, but I will just put it like 50. Anyhow, that's it. We don't do any starting sheets, none of these stuff. But we need to deal. Okay, minimize mass stiffness. In this case, we will do the stiffness. Or we can do two cases actually. One with the mass, one with the stiffness. But now I would actually enable also the buckling. I would enable all of them because we need, this is quite of a, even though it sounds really dumb, it's quite of a, it needs some calculations. And now we deal with the materials. Okay, by default, I would play mostly the metals and some ABS maybe. PAT is also an option, but I think ABS is stronger. I mean, of course, you need to know that like the more materials you put in, the longer the computation is gonna take. And it is on PAT ABS. Okay. Okay. Oh yeah, and I think that's also important is that like you can do the study settings and like tinker with this. How coarse or fine would the simulation be? Okay, so let's try our rock now. No, okay. Fusion really hates me today. And what if I run a new one? And this shelf that I have already, this is how this shelf was defined. Oh, you know why? There's a maintenance. I mean, look at this. On Saturday, March the 27th, Fusion will undergo a paint maintenance. Because it was working fine in the morning. I mean, I did a simulation in the morning and it was working fine. But still, I don't know. I don't know what can go wrong. So, because it was working fine. Anyhow, let me just clone this. Let me just clone this study. You can just clone it. Here it's set almost the same. And I will just generate this one. Let's see if it's to the setting or the servers. Luckily, all these are on the cloud, so I have, no, it's a fail. Okay, so it's a server fault because this one was working perfectly. Anyhow, we get some crazy shits here, but like, anyhow, one of these, this is one solution to it. And when you have this, like you can just like create a design from or mesh design. You can just like, let's create the mesh design. Let's see if that works. No, I can't. So it's a server thing. I can't even create the mesh design. Okay. So anyhow, you get this thing and you can flick through the iterations here. This is the 7th iteration. All right. You can see here how it actually started to morph it. So you see it always, when you don't tell him anything, it assumes it's a block and then it starts tinkering with the shape. And this is the last iteration. which doesn't mean that it has to be the best. I mean, always you have to like trust your senses, kind of. But this one looks quite stable. And you can also like filter them here through all of these. Volume, mass. I want to show all that are made additively. This one is made for additive. I don't know how these are gonna work because there is some kind of sometimes it gets really funky. It makes this kind of really baroque stuff. So like probably you can print this also, probably with a lot of tinkering and post-processing can support. Maybe if you change the orientation and stuff, maybe if it's printed like this and then a bit post-processed, probably. But this is far from the original result that we intended. And you can also, like, I want to compare this guy, and that guy. Let's see the difference. But these are all additive. I think there was some also. Yeah, not too much of a difference. Maybe some subtle details, except on this guy. But this one is from titanium, this is aluminum, and this one is Ilconel. So you can choose any of these and they should work. Anyhow. So do you want me to show you another example like this? I'm not running it because obviously the servers hate me in this time. I can explain you some other. For example, if you have a like the ones in the promo, like, or you can do some chairs. Like if you have this chair like we had, you can just take anything like this Eve's chair, right? You only need the okay. It can't retrieve it from the server. Okay, so Fusion is totally off right now because it's totally on the cloud. Yeah. Okay, so now we're going back to Rhino for sure. Right. Yeah.
Maybe you want to take a few minutes break.
Yeah, that's what I was gonna ask. Do you guys want to have a break before we continue on with the Rhino and stuff?
Yeah, let's do like 10 minutes.
Yeah, let's do like 10 minutes or so. Get up, like take a breath, leave the chair.
Yes. And thank Autodesk for doing maintenance on the same day as our webinar.
Yeah, and thank Autodesk.
Okay, so see you all back in 10 minutes.
The server gods are in my favor to opening another file. So guys, you're wrong. Anybody?
Is it thinking?
No, it's okay. I can show stuff. I can talk.
Okay.
I do not dare to run it, but there is some stuff like already ran. So this was the one that I ran this morning. So it was okay. But then again, at Autodesk servers, I guess in there in the USA, I don't know. Like it was Friday, so
Yeah. So what are you waiting to compute now?
I want to explain how this load case, how this is actually set up. This this is actually like this image with the base adapter. Where was it? I need to find it. Some made downloads. No. Free up space. Then, yeah, this not this guy. These guys. These guys. All of these are derived from these. Like, because you have a thing, in this case, this one went to the robot, to the TCP flange, and it made this kind of angled connection. So you can attach something here as a base. So you can make this to hold if you have an attachment for a pipe or for something else, or you can attach it like to this, because most likely you won't find I mean, you can also build a whole thing, but this one is kind of easier because it's gonna give you more flexibility to interchange stuff. But that doesn't matter too much. The point is, how is it set up? So we know that I mean, at that time at the lab, I had only like these big screws, which is logical because it needs to like literally be stable and go into the TCP, to the head, colloquially said. And these are the parts that needs to be preserved. All of these. This goes all the way. This goes, and the boundaries are like all of these stuff needs to be empty, and these are bigger because you need to fit your hand here. You need to fit your finger here if you want to screw it. So this kind of bolt needs to have an adequate place. And also your design needs to leave adequate space so you can reach in here with your finger and like tighten it up. So like the point is, and then how do you structurally simulate that? Now it's gonna be a more complicated it's gonna be a more complicated setup because like in this case you have a moving arm. In this case you have like, let me just draw this. No. In this case you have this arm and this thing with these is attached. Let me just change the color. And this thing should look somehow like this. Somehow. So in here you can attach new stuff. So in the very basic setup, it should look like this. And of course the bolts right here. So in the moment forces, like you have forces. Let me just do something more obvious. So you have like an arm that's moving all the time in all directions. It's not a constant load, it's not a constant direction. It's so you have to emulate more load cases. So you have like an orthogonal load case. That's how it's gonna be hit in one instance. It's gonna be hit like this. In one instance, it's gonna be hit in this motion, in this motion, and in this motion. And also their negatives, because this hand can move as freely as it wants. And like if you know what is gonna like hold or what's the actual purpose of it, you can dimension it according to that load density and stuff that we remember, which we inputted into topos and stuff, where they said, now I'm gonna set the load that it needs to be hit by concrete or whatever. So in that sense, we have the load case 1, which is which is this loads. Yeah, in this side. And this was it -x in this case. I just see this gizmos here, so where the axis. So and this x side, this is the first 12 case. And this force, it hits fx in this 37.5 newtons. So it's like 4 kilos or something. So because our robot is small, it doesn't have a big payload, so we can't really suspect that it's gonna be lifting something ultra heavy because it can't. So the loads are like quite small in general. So it's like okay. And in this case, it's only like 3.7 kilos in this direction. And that's one low case, but also these also put pressure on these screws. So there is some kind of a small moment inside all of these screws because, you know, as I said, with the simple shelf and like this swimming pool stuff, these will be a little bit smaller, like, but they exist and they need to like be calculated. Oh, in this case, I put them to save. Never mind. I mean, that's okay, but if you want to be truly specific, you need to, they need to be smaller. I mean, but there is no, it's not pain if you over engineer stuff. I mean, that's actually the first rule of engineering. Like you always design it with the maximum loads available. Like so, it's okay to go over the limit, but there's also over dimensioning. So like, you know, it's called also this kind of overkills and such. But anyhow, and you have as constraints these internal things, which you don't see now because of the obstacles. Yeah, these internal needs to be rings need to be constrained at all times. These are to be fixed because the screws need to go through here. Also here, same thing. Anyhow, you get all the load cases like that. So the second would be the forces going in the -x. And if we did this direction, now we're gonna do this direction. And also that also goes for the Z, this guy, this movement, and this movement. Same cases. And then we load all of this. I mean, we don't do any starting shape ever, right? We want the computer or the algorithm to find how to connect this together. I mean, and that's the big difference between topology optimization and generative design, because this is the true way of, let's call it generative design. You give him as little inputs as possible to solve the riddle. Wow. And I have it already done, so we can take a look at it. And we get something funky. This one is from ABS. It gives us something like this. Maybe it should be. Let's see what this one looks like. I mean, of course, you need to like at the end. Let's see. I think this one would be too thin. Maybe it needs to be sculpted after or something. Okay, that seems viable, although I'm not so sure about this. Okay, but that's only one group. We have this kind of visual similarity of groups. Oh yeah, I have to reset it. Okay, so the first group being some types like this. No. Okay, what's that? There was yeah, I think it was this. There was one that looked very good when I checked it out. I mean, these were like from the morning. I put this in the morning. This one looks rather sturdy. I kind of like it. You might need to like resculpt a bit here, but that's the easy part. And that's okay. I mean, they changed the algorithm a bit from the time I was doing the promotion. So I see different results now. Okay, that one looks nice. A bit thickening here, but it should be okay. Okay, that looks stable. It's created. Let's see if it gives me again or not. No, it doesn't want yet. Okay, what else? Uh, I see the question like in the chat. I still haven't tried higher values because like I haven't really had the time to really sit down and tinker with all the numbers and such. So I just like put relative numbers. So like because I'm not an, let's call it, civil engineer or something, or mechanical engineer to actually deal with this every day. So, but I do know the principles and what needs to be made. So it looks okay because like after this, when you like print this and stuff, there's like a whole another process how to print it, like which settings and such. So I think that's also quite important, quite adding to the durability or like performance of the thing, not just like the digital things. And also like, let me see if I can open the other example. This guy. No, could not open. Save. Okay. In this case, like in this case, I was making this for a scanner. Like so, in this base that you just saw, if that base comes here, like this should like stick to it. And you have this kind of thing. This should represent the scanner. So this would be the boundary. This has to be empty in each case. And you have the boundaries here and over here. So here we have the same story. The screws need to be here. And you have to have a place for your finger operation, let's call it. So this is all that it needs, literally. No starting shape, no nothing. And I'm just like gonna turn off the obstacles so you can see. And here are the actual places for the screws for the scanner. And in this case, because it's a scanner, you need to think now also functionally. It's a scanner, so it's gonna only move in 2 directions, eventually 3. It's not gonna experience this whole range of movement as the base adapter, because like the robot will be most likely programmed to like move in this kind of very controlled linear manner, so you can scan adequately. Because you know you can scan while moving it up and down or left or right or however. And in this case, like we have again the case with the multiple load cases, but in this sense we only have three, because I have been excluding one z-axis. I think it was the z-axis. Let's see. In this first case, it's the z, the negative z, I guess. Yeah. And the main pressure is here. You put your forces there, and all of these are constrained inside. But you also like need to put the moments here, because this is the same story as with the simple shelf, or with the swimming pool. But like these moments are now the ultra small, because the scanner is not that heavy, but still it makes some moments. And I have to click here. Yeah, I have done this movement, this lateral one, and the opposite one. Yeah, I have excluded one z. And the constraints are these inner circles, which have to be preserved for the screws. No. Okay. The criteria. Yeah, optimize the mass, all of that. In the time that this was done, these were not available, so now they are. We just manufacture them. Additive, nodes, all that stuff. I have literally done everything here because it's like a very general thing. And what does it say? And we got some crazy stuff. Let me show you. Compare. I like this one. This one. I'm searching for something different. These are totally unusable because you can't put the scanner in here. And this one is too thin. This needs to be thicker. It's titanium. I mean, I know it can hold it, but still, in my eyes, it's still. Oh, I picked all the titaniums. I should have picked different materials. This one is also nice. And would get this. You can see some of these. Let's hope that it can open. Yeah, this one can probably open because it's not a generative design. It's just a mesh. Yeah. So this is one solution. This one was made out of PLA, or ABS, if I remember correct. This was the plastic solution, let's hope. And no, this one doesn't work. Oh, it does. Nope. Don't save. No. But this one wants. This one was what? Out of metal. But this needs to be a bit tightened here. But otherwise it's okay. You can just like sculpt it somewhere. So, like, I mean, Fusion has also some sculpting tools, but it's not so intuitive. It's more engineering wise in this sense. I would rather do it in Mesh Mixer or ZBrush or somewhere just to like add a bit of thickness to this. I mean, unless you're actually printing it in titanium or something to test it. But if you want to just print it as a model at home in your PLA printer or something, I think it should be thicker. And now let's go back to the Rhino, because like Fusion is not playing nice, and I had to like explain you this advanced things. We should have done this on our own, like with our own modules and stuff. But thanks, Autodesk. So where did we stop here? We just made this. Oh, yeah, I need to clear this. I can also delete it. I have it exported anyhow. Okay, is everybody here? Or everybody just enjoying listening to me rambling around? Okay, so okay, so moving on. We stopped with this guy. Let me just bring it here. And the cool thing about this guy is now you have both the triangulation and the dual. And the dual is this hexagonal mesh. So the cool thing is that like you can just do mesh edges on any of these. And then run the multipipe. Not make it period. And you'll get some kind of a lattice, let's call it, outer shell, which is okay. You can also custom preview. Just work. In this mode or in Arctic, however you prefer. And you can add, you just make the node size a little bit smaller. One of the edges here. One. Okay, small. And it becomes a bit more open. And this kind of invites us, let's call it, to make the internal lattice too. Because right now it's okay. Right now we have this kind of external thing for our table if we're still like considering being a table. Ironically, I don't know why if you put these twice, like as a list, it won't work. Yeah, it will get you an error. That's also as if you were doing it with a list for all the interior edges and the lines and all of that stuff, it will still give you an error. So I just run it as this with a single node size. And you can like tinker with all of these, like how much would this strut between each other be, or like this kind of end offsets, segments. But I leave that up to you. Now I want to do the internal lattice. And I will do that with Crystallon, obviously. Just I'm gonna kill this one for now. Disable. And let me might shield a few back. And with Crystallon, that curve, and somewhere far in the back. See here. You have this kind of tabs, and you start with like voxelizing your geometry. And we're gonna be voxelizing by parameter, let's say. So we just like input this geometry, one of these, and we need to like set this, like we can just, well, I mean, you can just do it randomly, and this would be the P box, so we already have it. This would be the P box. We just extrude the bottom surface of this. And that would be the plane. Nope. And triangulation is here. And this would be better to be data. So we can orderly. And then we need to set the parameters. We just get a reparameterized range. All of these. XYZ. And just make some steps. Okay, there should be more voxels here. Or we can just like fill completely. We can try it out. I think there should be more because there's some weird stuff here. Yeah. or just run it as basic as this for testing purposes. I mean, we can also be ultra proper, actually, like deconstructing this box. And we get the X and Y that domain. The domain. I want to see the distance, like the proportion between. Oh no, what? But the main goal was like, my thought was to make these not on a single thing, but more balanced. But let's see how it goes with this. Actually, we can do that if we just get the lines. Highest and the lowest. But this data, I need it to be absolute because I want to compare the pure number, not the pure value. That's what. Maybe or we can just like entwine it. Less components. Maybe it's not that ABS. And all of these need to go to this. To divide. So 1 point, not too much of a difference. No, it's not worth it. So we'll just stick to these, I guess. We can also try, we can try. Let's look at this. Just this. What does it say? 6.5, 6.7. Nah, it's all gonna be rounded to 7. Because we need the actual steps. 7, 6, 7. Big deal. We don't need. Anyhow, we get our voxels. Oh yeah, just reconnect this. Get our voxels and we need to populate them. We're gonna be doing a lattice. These are our voxels. And now we need to choose something. So selector. This would be the selector. And cell type to preview it. So we get this kind of one. You can choose some of these. I would propose choosing something without a cage, something without this. I mean, in our case, it's gonna just create a big of a mess. So either some of these stars. This probably could be also nice. Octahedron. Or this. Maybe also this would be nice. Just don't do the shells. We're not doing shells right now. So I would just like do the ultra basic one for the sake of not torturing my computer and the stream. And we have the whole thing latticed. But as you see, it's still rough. It's still too square. We need to trim it and modify it a bit. So what do we do? Where was it? Move floating. Trim. Yeah, trim that. We have our lattice. This is our original path. This is our. Let's take it from this data. And we have it, our lattice trimmed. And now we can move on to, you can either sort like, remove the floating lines. Okay, so everything is floating, nothing is connected, which is not that scary or not. We'll see. Can remove shorts, but I think they're all the same because of the nature of the lattice. Yeah, more or less. You can see that. Okay. Smallest one being very small. So let's just take the average. Yeah, so this would be the average length. So we're missing quite a lot. Let's just say 1. There's a lot of small pieces. Let's see. Yeah. This one. So that means we definitely need to make more blocks of. And just disable this part so it doesn't go crazy. And save. Kind of don't like that it's kind of starting to connect. But maybe when we trim it, it will go away. Let's see if it's double. Okay. At least most of the stuff are connected. I don't really bother about this too much because I'm gonna put it in the multi-pipe later anyhow, probably. And we can just thicken it. So it will probably connect. Anyhow, let's do some thickening. You can also, there are two ways now actually. You can either use these. It will give you some values, which you can like just do an in pipe or some other pipe, or also fatten. It's also nice. Or the regular pipe or any pipe. Or you can just do it yourself. Like from maybe all of these lengths, I want to like reparameterize them. First, I'm gonna take a couple of them actually. Let's see, I just take 10. So I can see the values. And when you put these, it also the 10 values. something here. Okay, that looks pretty fat. So just like prepare and trace numbers. Nope. And trace numbers, but this will only give you from 0 to 1. I mean, this is the dirty way to do it. The proper way is to like actually remap the numbers with the remap numbers component. Because this will also give a 0, and you can't have a radius of 0. So I have to like add something small. What's the smallest? Zero, oh, obviously. So what's the second smallest? And we choose that. Let's add the second smallest. And let's see. Oh yeah, I forgot. Which should be here. Okay. Yeah. There's an obvious difference. So let me save. Okay, it's now it's all radius of 2. We get a lot of blobs. Ah, okay. This is the lattice we need, actually. Because the other one, it's the ones that have fallen away from the geometry. You can use them probably for something if you want to use them as, I don't know, external decoration. I don't know. This needs to be a data. Okay, this one goes here. Okay, too low. Might be. But anyhow, that's not my point now. I tried, I like to use it with the multi-pipe, or we can also try it with the pattern. Oh, how come there's a lot of zeros? Okay, I will do this like this. She said, and then sort it. Okay, it's not first. Okay, 0, 1. First 0. Okay. So this guy, like that. But it might be too much. Let's see. Will it crash? Probably. I haven't used this mesh pipe and pattern for a while though. Ever since I discovered this multi-pipe, I have been using it much more. The results are much smoother. I mean, you get a sub D afterwards, but still, it's much smoother. No, I would kill it. Okay, whatever.
Zvonko?
Yeah, I'm here.
Okay, I just didn't know if it looked like it froze.
Save. I made a dumb thing. Should have disabled this. Is it? No. Oh, Okay. All this. I mean, I want to also, I mean, we're pretty much done with the lattices, pretty much. Uh, I wanted to show you how to animate stuff, how to animate this process in V-Ray, or how to animate it in general. So that's not too much of a time. Unless you want to like tinker with V-Ray, that's not too much of a time. So Mike, what do you say?
Yeah, I mean, I don't take as long as you want. I mean, if
Mm.
you know, if people have to go, then it's
They have
they
the
can watch.
recording.
They
Yeah.
they can just watch the recording. If you have to go, just go. Um, so that lattice crashed. Is that what you're trying to open the
Yeah,
file
yeah,
now?
but no, I disabled it, but like it's because it's computing everything, you know.
Yeah, yeah.
But, but the lattice shouldn't be a problem. Yeah, it's okay.
Yeah.
Okay, what do we get? Okay, we get a, oh, now it needs to be reset. Oh, okay, everything seems to be breaking down on my PC. It had a hard day. Okay. Okay. We get our table back. Is it different now? It seems a bit different. This part wasn't there. I don't know. Let's just like bake it. Or at least internalize it. For the safety. Okay, all of this. Control. Okay, that works, that works. We have something, that's cool. Let's do the multipipe, it's faster. I'm gonna combine both multipipes, both lines actually. As we have this external thingy here. I'll get this. And we get this one, the internal. I'll just merge it. What did I put? 0.25. Okay. Let's do 0.3. And now multipipe should connect all of them. Oh yeah, that. And we get our lattice thing. Much more smoother than the M pipes and stuff. Okay, that looks fair. Do I have another custom preview somewhere? No. Okay, so that's the thing. Yeah, and inside you can see the structure. That looks cool. Can also make it a little bit less dense. What was it? 0.25. Okay, more open. Okay, that might be too much, but the internals are nice. You can see more of the internals. Okay, so I think just because this one is remote, I can just add it to your topos start. Oh, no. So you can because now we're ready to do the animations and stuff, like tinker with the visual a bit. Just add this thing here. I don't need any of these. Okay. Same thing. Okay. Back to the one. Put this. Yeah. Where's this? I'm putting it to the Dropbox now. Okay, it's there. It should be updated. Just re-download it or something. Anyhow, let's continue. This might be right. Like, there are two ways actually to do this. You can just like flick through. Well, okay, I'll do the simple one and then we'll mess with the topos. If there is enough force in my computer, so to say. Not anyhow. Where's my viewer? Can something. Yeah. Actually, you don't need to set it up because by default, it will just take this like viewport. So the important thing here is to like get the viewer render. And we need the viewer timeline. So what I'm going to set up now is actually a really simple color changing animation of this, or material changing, however you want to put it. You can do it both ways, either colors or materials. In this simple example, later we will try to actually animate the topological generation. That's why the topology optimization. If my computer is up for it, as it started today. Anyhow, we need the material preset. So this is a basic material. We're gonna feed it something. And like the preset, you'll see you can pick whatever you want. I'll just choose it's a metal. And it will give me a generate metal. But I want to tinker with this material based color or texture. So I'll just like make a gradient. Let's say it's whatever this one, or choose anything. This one will be better. This is custom, so like you can choose whatever you want. But this is a gradient. Okay, I moved it. So we need to synchronize this current frame because this is set to 30 frames or something. You can also set it to as much as you want. Set it to 15 for faster. So I just get the basics of this. And you have the range start and range end. Right. But in any case, it will give you the current fraction. So, and the current frame. So right now it's on 0. And this should be 0. And as I move, it should be slowly creeping up to 1. And that's what we're gonna use in the parameter. We get a color, custom preview. So our custom preview from above. And that's the thing. In Arctic mode, I can't really see it. I could have seen it like from some update ago. It got screwed. I can't see the colors in Arctic mode. I can see it in rendered, but I couldn't see in Arctic. Anyhow, and when I click this timer, this should happen. And you can also solve this another way. And if you're too, I don't know, if your computer is too slow or stuff to render this animation sequence in V-Ray with the proper lighting and materials and all of that stuff. You can also use like this FroGh, which is also quite nice because it gives you this kind of camera control. And what is it? Camera report. So I think you also have this in the V-Ray camera, but I have known this method before I knew V-Ray. So if you go to toggle, or I will just get back to this later when I put this animation to run. So we get this material. We put it on the metal. And we need to like do this V-Ray geometry. There was the V-Ray geometry. So we need to put the material here. And the geometry is our guide. Okay, we'll just put it into data. And this guy is in here. And we got our compiled V-Ray geometry. You can leave all of these by default. It will just pull it from the Rhinoceros CD, unless you want to like deal with more complicated light setups and stuff. But in this case, we don't really have the time to mess with that. And this timeline goes here. And oh yeah, you can also do this show controls, and you will be shown all the controls. So it's CPU, which is okay. You can put this to production. Progressive, medium, I would set it to low for now, so it just goes faster because we don't know what we're getting currently. And the output image, it's a file path. I'll just make it here. And if you do it as a PNG, it will like render it with a alpha, with a transparency. Or just do it as a JPEG for the, just for the having a background in between and behind. One. Progressive, okay. Let's see what we get. Oh yeah, the output resolution. Right now it's some resolution. I think it's the one that's here. When you go to the V-Ray and stretch these, I think it's this one. Or was it camera, not camera, render output? Yeah. 800 and 450. Yeah. But I have also like given you, I think, this plugin that plugin, component that I wrote, like get viewport dimensions, because my viewport is smaller currently than usual. It's some odd number. It's like 732 by 805. So I'll just use that. I just need to make it into a list. Like merge. Okay, just make sure it's always flat. And you can also enable the save frame, I think here, so we will see. There it is, maybe here, and also make it match the viewport. And let's see what gets affected. Let's do a thing. Doing no. Nothing there. Okay. Disable true. Or did they put a light, or it just put no? Oh, because it's a sub D. I don't think it will recognize a sub D. Sorry. Sub D from mesh. Or mesh from sub D actually. This is reset. That's okay. Let's see. Okay, now we have something. It's okay, it matches. That's fine. Go a bit side. You should be seeing it change colors. And yeah. And here you can automatically like add a bunch of layers, like this kind of Photoshop layers for like display correction, like lens, like I don't know, all these curves and adjustment to the brightness or whatnot. You see this color balance, hue, white balance, whatnot. You can just click and play with these. Which frame is it? 3. God damn it, that's slow. Why is it stuck? I should have put it on the interactive. It would be faster. And it jumped to 10 suddenly and changed the color. I wanted to continue with the other animation style, but I guess Vue won't let me. I think it's done. I'll go here and I see all these. I have this kind of animation on the whole gradient. And what I will do actually is just like open Photoshop. And you can also do this online. There are some GIF makers where you can put your pictures and stuff like that. But I find Photoshop to be faster. You just go to scripts, image, not image processor, but load files into stack. You could select your files. All these guys. Okay, still working. Okay, we're here. What you do is like, I need to open up this timeline. I need to just to create frame of animation. And I'll select all of these guys. Make frames from layers. Probably reverse it. I don't know what, from which end of the spectrum do you want to start? What was here, which was the first? This one is the first one. So it's reverse, actually. Reverse frames. Or maybe just kill the first frame. It's too out of the spectrum, let's call it. Yeah. And you can just like preview it like that. Oh yeah. Just want to make it much longer. Just select them all with shift. And do like, I mean, here you can actually calculate it. You know, like if you want it to be 5 seconds and like the average I like can spot differences at like, I don't know, 20 frames per second or 30 frames per second, you can actually calculate that. If you want it to be like 35 seconds, 5, that means like it needs to be like 6 frames at a second. So 1.6, sorry, 0.166. This should be the rate of the moving of the frame. So it's like 0.1 is okay. I was rather correct. You can also do other and to be like ultra correct. And now we have our animation. And you can just loop it once. Let's say. And plus, now you're in Photoshop, like you can cut it, edit it, do whatever to it. And maybe I just want this to be the animation, whatever. And then when you're happy, you just like export, render video. You can also like save for web if you want to make a GIF out of it. You can just save for web and you can export it as a GIF. But if you want to like have a proper AVI or something, you need to do like render video like MP4 or something. Yeah, MP4. And you can optimize this as you want, as much as you want. High quality, low quality, YouTube, Vimeo, whatever. I'll just leave it as it is. We don't care. And in this second, doing the video, and that was it. Short. And it's also like the dirty hack is if you find it too short or something and you don't want to bother with this math stuff, you can just like also copy this. And like that's the dirty way. And you will have it twice. Or not. Or maybe I just didn't do it correctly, but you get the point, I guess. Or maybe this one should be 0.2. Anyhow, I don't want to waste too much time on it. You'll get it. Anyhow, what I started doing here, you would get this. This is the V-Ray way. If you want this exact same Arctic view, you're better off with FroGh. Where did I start doing it? Yeah, this camera report. And you get the exact camera location. You get to this. You capture the file. And you get literally the same thing. Just image size, viewport name, file name, file path, grid axis. And like you would get the same thing, but just from this exact view, not rendered V-Ray and stuff, but you will see, you will still get these files. And you will still have to do this kind of GIF making or video making. And here you can also like do it with the animate slider. And now, yeah, then it would take a bit more math, I guess, if you have the like reparameterized range. And you want to do it right here. Yeah, and then you just like replug this here. And this needs to go here.
Hey, Zvonko,
So,
what do you say in like 10 more minutes
uh,
to do Q&A?
yeah.
Okay.
Yeah, so like that would be it. So like I mean, important to note also that you can change this. This doesn't have to be, I mean, if you have built this properly in V-Ray, like with proper V-Ray materials, I mean, I want it to be like properly metal. Like this aluminum or titanium. You can also add the glass here. I mean, maybe you just like build up the glass with, I don't know, proper faceting and stuff. You can add that one too, but right now we don't have the time. I have done this here, but that was for a bigger model. Anyhow, my point was like when you have these referenced and they are into your scene, when they show up into your scene, like here, you can reference them. No, Not rendering projects. Very material from project. What is this loaded? Okay. So you get titanium here. And you can just like switch this instead of our own. And when I do the simple render now, like a single render, you will see it now in titanium. And you can also like make it switch. Like if you have 3, let's say, or some X amount of materials loaded here in this 16 steps or this range, you can probably set on each step like to emulate a different material. But that's more time consuming and probably will take a while to build up. So this with this preset is much more fast, and it's equally effective, I guess. And it's going to be also like this. You can make it glass too, or whatever. It still has this kind of metalish look. And you can set it to interactive, not production. So you can deal with it in real time. Now, I want it to be, let's see, glass. That also works okay. Plastic for whatever. I like the metals. So. And you can also export it to V-Ray Vision. V-Ray Vision is like quite nice because it's this kind of live link, like Inkscape or something. You just do like your live link. You just put your scene here and start video revision. I mean, but this is more effective if you have something large, like a house or something. And now you can see it and move around it. And maybe the light, we haven't set any lighting, so that's why it's so dark, because it's like the complete setup. But anyhow, like now you can just hover around, but you can also change like camera navigation, and you can now just do WASD and walk around it. You know, this kind of Inkscape, Unreal Engine kind of hero. So basically it's kind of a gamified engine. And you can, yeah, automatic exposure and all of this standard usual suspects. But this works much better on a bigger scale if you have urban plan or architecture or something. But this one is okay. See. Okay, so this has been already like too long, so I don't want to like drag this even further because like there's like a lot of stuff to talk about. And plus we had these delays from Autodesk and stuff. So that was the Easter egg. It's almost Easter, so we get our eggs early.
So do you want to move to Q&A?
Yeah.
Okay. Well, thank you. This is really cool to see. You know, I would just say from my end, the big kind of takeaways is you definitely want to have the right kind of computer and cloud computing for this kind of topology optimization and generative design. So yeah, like, you know, don't expect to do it on like a low end computer in a very easy way. What would you say?
I would say unless it's like totally 100% almost on the cloud, like if you use this wagon or something, this paper space and stuff, if you've heard about that, like they just give you a Rhino on the cloud or something. But of course you have to pay for that. And you can run it from almost anywhere. But still, all your data is there, all your data is in the cloud. And
Okay, so does anyone want to ask a question live or come on camera and ask a question or discuss anything? Just click the raise hand button and we'll add you here. Or you can ask questions in the Q&A. But it's always more fun when you
talk
on the camera. And we can see also if there's any. I don't know if you want to put your camera back on also.
I have a really bright background, so I need to put my head on it too.
So let's see. We have there is a question like, what are some popular industrial design objects that implement topology optimization and generative design? I don't know if you answered that one, but I think also the important is the distinction between the two, where topology optimization is you have a geometry already that you're optimizing, whereas generative design is you don't have a geometry. Like the geometry is being made through things like loads and forces. So it's more like kind of being made in a field through analysis. Like you're not really starting with an object.
Yeah, I mean, that's the thing, because like with generative design, you're starting with scratch. You just, as you saw in the Fusion examples, they look really empty, right? Because you have only the ultra basic. Okay, I need to put the screw here. It needs to connect to this, and this. I need to have this plate available to like put my, I don't know, scanner and or like whatever I'm holding or doing it for. Like, and that's it. That's all it takes.
We have a question from Walid who's saying, is it possible to make this model with all these openings? It's already possible. I mean, it already exists. Like, you just look at like
Yeah,
Joris Larman.
yeah, you're Islam and stuff.
I
Yeah,
think he
I
has
have
a
seen a
bench
lot
that
of
has
these.
like the same exact topology almost.
Yeah, I mean, this is totally doable. If you, especially with a robot like these MX3D robots and stuff, and or any robot that's like has this kind of extruder. Let's call it. You can totally do this. I mean,
Yeah.
it's doable.
Yeah.
That's what I mentioned in the beginning. It's not like it's not a question anymore if it's possible. Like it is possible, like, but you just need to like find the right equipment for it.
And the
For
right money.
yeah, and the right money. Yeah, and somebody willing to pay for that. Because, there's a lot of these stuff in the lab state, let's call it. I have seen a lot of these stuff that's hiding in some research lab somewhere, but like don't really see the light of like commercial like being. I mean, they might exhibit it at some fair or something, but like it doesn't really go too much after it.
Yeah.
But it's possible. That's right. Especially with robots, you can do all of these, like all of these CNC holes and stuff. Like probably the robot you even can CNC the whole thing. Like if this is a huge chunk of, I don't know, ABS or whatever you want to make it out of, like you can pierce all of these holes, or you can just print it like layer by layer by layer and stuff. And you can then specify in the slicer or in the G code, however you're doing. Like I don't want any overhang to be more than 45 degrees, because otherwise the stability and the statics of this thing would like crumble. And take a look how they made the bridge in Amsterdam, MX3D. Like they have a really nice animation of that.
Let's go. So this question here, someone's asking you if you ever tried to CNC some of these pieces. What's the best
Yeah.
medium for that? And I would say, I mean, this stuff is really meant for like additive manufacturing, not really CNC.
You can, like, because
Yeah. But I mean, if you have access to additive manufacturing,
yeah,
why
yeah,
make all those molds?
yeah, and plus like you have I have never seen a more than 3-axis CNC, honestly. Like, I mean, for everything else you have a robot. The robot is a 6-axis CNC or a 6-axis printer, so like it's
Well, the problem also with
more.
the CNC is all those parts inside. It's not
Oh
really
yeah,
like,
oh yeah,
it's not really an object you can demold. You know?
yeah. It's just there. I mean, economically, probably it's much cheaper for somebody to own a CNC, but like, I mean,
I mean, like, how would
uh,
you, this thing, like, for instance, the bench on the screen, like, you would never be able to pull that out of a mold.
yeah, no way,
It just would
no
be
way,
impossible.
no way, no
Yeah.
way, no, especially with these inside lattice and stuff.
Yeah, it's
No way.
because, you know, with CNCs, you got to always thinking about undercuts and
Yeah.
pulling the thing out of the.
Oh, yeah, you have, yeah. CNC is sculpting, literally. You are like, I don't know, Leonardo da Vinci or whoever, and you need to like sculpt your piece. Right.
Yeah.
And like here you're free. Like, but then you need to know the materials much more better, because like they have all the temperatures and like mode. Like I know when we were doing scenes like spraying with our robot in the lab, and like you need to have a really consistent environment to be actually to be able to spray, because the concrete needs to be at a certain humidity, it needs to be at a certain like room temperature and stuff like that. Otherwise, it won't spray. It won't spray properly. It will get too hard when it's spraying. It's the same with printers too. Like if you let too much filaments out on the open, they will get moisture and it will not extrude properly. Like I don't know, like with my printer, like now I'm gonna do a generative like box for this guy, because this is a filament case, and I plan to like mount it on that guy over there, because when printing some filaments like polyethylene or something, it absorbs too much moisture and it won't produce good prints. I mean, you will see the blobs and this kind of rough texture, and it doesn't look nice. I mean, it will probably print, it will probably make it stink, but it will be like really shitty. I don't know. You have to see it. So like, it's not gonna be visually nice if you're doing for the aesthetics. Yeah, I mean, if you're just doing functional parts, then maybe you don't care too much, but still you will see the stringing and the rough surface, and it's generally not nice to see.
We have some questions about Fusion for like topology optimization for architectural areas. Curious, like for instance, the skeleton structure of the tower in the 1000 museum. But again, like that's topology optimization.
Yeah, that's topology,
not generative design.
Yeah, no.
But also, yeah, I mean I mean it's architecture office. I mean they definitely like modeled that with some kind of intent and then maybe optimized it structurally after. But there's
but
they knew beforehand like what the geometry wanted to be.
Yeah.
So it's not really the same
It's
idea.
not really the same, because I mean you can probably generate some parts within, like you know, like if you have like I need this like element to fit the railings, I don't know, or some kind of a
or even
spider web or whatever.
If they had everything there except for the structure, and then used everything that's part of the building as the load calculations on like a solid wall, and then whatever that wall became would be a generative designed wall.
Yeah, or some furniture inside or something. But in panels and in modes and all that stuff, yeah, for sure you can do it, because you have quantitative things that you can like measure. You have some stuff that you can like base your design on.
I guess in that case, you'd be measuring like the weight of the floors, the probably wind forces, I don't know, all kinds of, whatever has to do with
whatever
structure.
literally. Yeah.
And then just let the algorithm like find the connections and eat away at the solid until it's kind of this minimal remaining shape.
Yeah. In that case, you can.
Yeah.
But
and that brings us to another question: Is Fusion useful for bigger objects such as walls?
Yes, I have done columns, and like with some students in my studio in TU Berlin, like we did these kind of highway columns, like which are like.
I remember Autodesk doing it also for the structure inside of airplane partition.
Yes, for airplanes and for bikes and for all of this stuff. Yes. But you can also do columns. You can also do architectural elements. You can do benches. Why not? Like.
Can you recommend some resources to get more information about how to define forces and constraints for more complex objects.
Yeah, that's the thing. Me myself, I haven't mastered it yet because I haven't had these proper engineering classes, or I had them like 5 years ago or so when I was like actively studying.
Yeah, I mean, there's not going to be anywhere online. It's just going to like give you the
No.
answer.
Not really. You
That's
have
why
to,
there's structural engineers.
yeah, that's why they're structural engineers. Yeah, that's the right answer.
Oh, because they know the math, and like
Yeah.
you just have to, because it's not like you just use the same situation, right? Like you have to know the math and what you're measuring, and um,
yeah, but you have to develop this kind of sense, which load comes there, which moment goes there, what would happen in this kind of system, like.
so in terms of like resources to get like more information, so defining them for complex objects, I mean, that's honestly more the situation where you would really like a college class, like degree and
yeah,
and studying. I mean, because that's the kind of thing that people are really like, spending
yeah,
5 or more years of their life studying, so it's not going to be just like,
yeah, it's the same as learning programming or Python or C# or whatever. You won't expect to find a resource that just tells you, okay, do this, and you will like learn it in, I don't know, 1 hour or whatever.
and so like then now they're asking like, so that another part is that, so example, Morteza has a pavilion, and the joint pavilion has 3 pipes arriving in a point, and this joint holds 3 pieces of wood, but I don't know how to find the forces and constraints. And so I guess like if it was me, I would probably try to consult with somebody that is an engineer, to tell you what kind of forces you should be looking at, because there's like, moments and gravity and torsion and all these complex forces.
Yeah, but that's in general, like it's software independent, like whether you want to use it in Rhino or in Grasshopper or in Fusion, or you will hit that wall at some point, like.
Yeah,
Because
that's a good example, actually. It's software independent.
yeah, but because like if you go to do the same thing in Karamba or in Millipede, whatever, you would run into the same things. Like you will still need to set up the forces. You will still need to set up the moments. You will still need to input all of these density parameters, whatnot. It's the same thing. It's just the algorithm is different. The workflow and the things that it gives you is different.
Yeah, like all these softwares are like pretty stupid, right? They're just like listening to your instructions, but if you don't have the experience for that specific set of instructions, then it's like, because the algorithm's just going to solve whatever you give it. Who's to say that this value is correct or that value is correct?
Yeah, the computer is blind and dumb, literally.
And then so we covered like architecture. So the only other thing is people are just asking about the files. Here, I'll put these files in Dropbox.
Yeah, I don't know how to share Fusion files. I haven't shared Fusion files so far.
Yeah, that's the hard thing about Fusion, because it all lives on the cloud.
Yeah.
It's not really easy to share.
Yeah,
Fusion.
that's the benefit.
Unless you're part of that person. Yeah, unless you're part of that person's like cloud network or.
Yeah, it's kind of difficult.
What's the point of Fusion in this case?
Yeah,
Fusion.
This said, kind of.
For generative design. Fusion is doing generative design. In this case, computation, which is not an easy computation. And I can't think of any. I mean, tOpos isn't doing generative design. I don't know.
No. I haven't seen anybody in
No, there's no.
Grasshopper anything that actually does generative design.
And when we say generative design, we're talking about like what Autodesk calls it.
Yeah. That's the true generative design. The other ones are just like the loops or whatnot.
Yeah, everything else in Grasshopper is kind of what you can call topology optimization.
Yeah, kind of. Yeah, or force modeling.
Yeah.
You have already a predefined thing that you just hit with forces, but you already have the thing. You're not. The computer is not inventing it for you. Let's call it.
They're saying you can use .f3d format to export.
Okay.
If you want to try it, it's up to you.
Yeah, I'll see. I'll tinker with it.
Yeah. Just mess it, and you just put it in Dropbox after.
Yeah.
Okay, so I think that's pretty much it. Unless anyone.
There's one. I know. Did we cover this?
Which one?
No.
Unless anyone wants to talk live, I think we should end it because we're already over an hour.
Yeah.
Okay, so let's end this, and I will send. You'll get another email about the recording and certificates. And yeah, I'm glad you all enjoyed. I know it's a lot to take in, but these are tough topics.
Yeah. As with any new thing, like.
Yeah. Also, check out our resources page on our website because we have some like intro to Fusion classes on there. But you know, the thing with Fusion is it's one of those softwares where you can very quickly end up needing to spend money to use it.
Yeah, if you're using it commercially.
It's just the way that, whether we agree with it or not, just the way that Autodesk has set up that software.
Yeah, but yeah.
So, but we definitely have like Fusion 360 for beginners on our resources page, which is here, and yeah, cool. All right, well, thank you everyone for joining. I'm gonna end this. Thank you, Zvonko, for taking the time today. It was really insightful to see the kind of inner workings of that.
No problem. It's been a pleasure to like talk to you.
Okay, bye everyone.
Nice discussion afterwards too.
Yeah.
So like, so see ya. See ya, guys.